We now go for question number 37. See, now we are going to see some of the applications of Gauss law. We would like to find out electric fields produced by infinitely long straight line of charge having uniform linear charge distribution, then infinitely extended plane of charge having uniform surface charge distribution, then spherical shell of charges, then sphere of charge. So, we should consider 4 charge systems: line of charge, plane of charge, shell of charge and sphere of charge. Line, plane, shell, sphere. Let us see one by one. Okay? Come on. Infinitely long line of charge having uniform distribution, or infinitely long, extremely thin and straight charged wire. You may think of infinitely long straight line of point charges, say all of them are positive, having uniform linear charge distribution. If charge distribution is linear and uniform, then linear charge density lambda will be constant throughout the length, correct? Fine. Now, we would like to find out electric field produced by such a line of charge. For that sake, what we do, we just consider some convenient Gaussian surface which can enclose some part of this line. Okay? I am just considering such a Gaussian surface in the form of a closed cylinder having radius say r and having length say L. Okay? Fine. Now, this much charge from here to here, the charge containing this much length is enclosed by this closed Gaussian surface, and that enclosed charge is suppose Q and corresponding length is L. And you must remember, charge per unit length is nothing but linear charge density. Okay? Fine. Now, just to find out electric field produced by such a line of charge, what we do, we try to find out first of all electric fluxes linked with 3 parts of the Gaussian surface. Which 3 parts? First part is this, which is planar surface on the left end. Second part is this, which is again planar surface but on the right end. And third part is this, which is curved part, which is having curved surface, correct? Fine. Let us see one by one. Remember one thing, for infinitely long straight line of charge, remember, electric field is always perpendicular to that line. Electric field produced by infinitely long straight line of charge is always perpendicular to that line. But if it is positive charge, electric field is away from it. Had it been made up of negative charges, electric field would have been towards it. Right now we have considered positive charges, so I am showing electric field away from it. Got it? Fine. Now tell me, according to general formula for electric flux, it is integration E dA cos theta. E dA cos theta. Here strength of electric field I am taking E1, then area vector magnitude I am taking dA1 cos theta. Theta is angle between area vector and electric field. Area vector for this vertical plane will be like this. If this planar surface is like this, what about area vector? Area vector will be like this, perpendicular to that, correct? And for a closed surface, it is perpendicularly outward. What is angle between this area vector and this electric field? It is 90 degree, and cos 90 degree is 0, correct? Similarly, phi 2 equals to integration, come on, instead of E1 I am writing E2, instead of dA1 I am writing dA2 cos theta. Theta is now angle between this area vector and this electric field. For this surface, if it is like this, what about area vector? Perpendicular to that, like this, correct? Again, angle between these two, you can see it is 90 degree. When angle is 90 degree, cos 90 degree is 0. So, this electric flux is also 0. What about electric flux linked with third part of this Gaussian surface? I am showing you. Consider some area element here having area dA, but so far area vector is concerned, you must show it perpendicular to the plane of area element, and that too for a closed surface perpendicularly outward. And so far electric field is concerned, just now I said perpendicular to line of charge, but because it is made up of positive charges, perpendicularly away from the line of charge. Correct? Fine. Now here angle between vector E and vector dA, it is 0 degree because both of them are pointing in the same direction. Now come on, integration E dA cos theta. Theta is right now 0 degree, cos 0 is 1, and now because value of E is same at all these points which are equidistant from this line of charge, the magnitude of electric field is same and constant. Because value of E is same and constant, I can take it out of the symbol of integration. Come on, take it out. Then integration dA, integration dA. Now E as it is. What do you mean by integration dA? Integration dA means summation of areas of all the area elements chosen over the given surface. Right now given surface is the curved surface of that Gaussian surface, and that curved part is like this, and for that curved part, what is the total surface area? Total surface area for curved part is 2 pi RL, 2 pi RL. Come on. So this is going to give me area of curved part which is 2 pi RL. Fine. And now tell me, what is the total electric flux linked with this closed surface? And that total electric flux is suppose 5, then using Gauss law we can find it out. According to Gauss law, it has to be Q upon epsilon 0. Phi equals to Q upon epsilon 0. Phi equals to Q upon epsilon 0. Correct? Now what is this phi? Total electric flux. It is made up of 3 amounts of fluxes. Come on, phi 1, phi 2, phi 3. Just add up all these flux values, phi 1 plus phi 2 plus phi 3, and that equals to Q upon epsilon 0 as it is. But what are the values of phi 1 and phi 2? They are 0. What about phi 3? It is E into 2 pi RL. Phi 1 and phi 2 are zeros. Phi 1 and phi 2 are zeros. Correct? What about phi 3? Phi 3 is E into 2 pi RL. E into 2 pi RL. Correct? And that equals to Q upon epsilon 0. What about Q? Q is the amount of charge enclosed by that Gaussian surface. Come on, find out Q from here, transfer this. Q equals to lambda into L. Come on, this Q is lambda into L. So replace this Q by lambda into L upon epsilon 0. Now tell me on both the sides, L and L will cancel. Now find out E. Take this 2 pi R on the right hand side in the denominator. So now it is lambda upon 2 pi epsilon 0 into 1 upon R. Into 1 upon R. Now this part is constant. This part is constant. So if you think of relation between E and R, that relation is E varies as 1 upon R. Electric field produced by infinitely long straight line of charge is inversely proportional to perpendicular distance from that line of charge. Okay? And when E varies as 1 upon R, in that case, if you plot a graph of E versus R, that graph not given in the textbook, just for your kind knowledge, I have drawn here. The graph is like this, E versus R. The graph is like a hyperbola, like a hyperbola. Remember Boyle's law? Boyle's law, P varies as 1 upon V. P varies as 1 upon V. At that time in 11th standard, you were drawing graph of P versus V. That graph was also hyperbola. Similarly, here E versus R, that graph is also hyperbola. Correct? Fine. And this is the magnitude of electric field. If you would like to have vectorial form of this same result, you can just write vector E. Correct? Instead of E, you may write vector E. But don't you know vector equals to magnitude multiplied by unit vector. Magnitude is this much. Correct? Same magnitude I have written here, multiplied by unit vector. But that unit vector must be in the direction of electric field. Direction of electric field is right now perpendicularly away from line of charge. So in the same direction, I must write unit vector, and that unit vector is r hat, which is a unit vector in the increasing direction of r, in the direction of increasing value of r, in the direction of increasing value of r. So this is the unit vector in the direction of increasing value of R, or you can say in the direction of electric field. But mind well, we have taken positive charges in this line of charge, but instead of positive charges, if you have line of charge made up of negative charges, then electric field is pointing towards it. At that time, instead of R hat, you must write opposite unit vector, that is minus R hat, minus R hat. Got it? Now we go for question number 38, that is finding electric field produced by infinitely extended plane of charge having uniform surface charge distribution. Fine. Consider this a small part of infinitely extended plane of charge having uniform surface charge distribution. Out of that, I have taken here small part. Fine. Now we have to find out electric field produced by such a plane of charge, correct? This is a sheet of charge or a plane of charge in which I have shown all point charges to be positive. Fine. For such a plane of charge having all the charges positive, remember electric field is perpendicular to plane but away from it, perpendicularly outward or perpendicularly away. Okay. Had it been made up of negative charges, then perpendicular and towards it. Right now made up of positive charges, so perpendicular and away, correct? So direction of electric field on this side will be like this, on this side will be like this, correct? We have to find out magnitude of that electric field. How to find out? I am showing you. As shown in the diagram, you just consider a convenient cylindrical Gaussian surface whose axis is perpendicular to this plane of charge and whose both the halves, equal halves, are lying on the either side of plane of charge. I would like to show you exactly in the diagram, I mean the physical situation I am showing you. You can just consider this board as plane of charge and consider this as closed Gaussian surface which is cylindrical. Now you can see the axis of this cylindrical Gaussian surface is perpendicular to this plane of charge and its a half part is on the left side, remaining half is on the right side. Got it? For this plane surface, tell me, how would you draw area vector? Perpendicularly outward like this. Say this arrow is area vector, then you can just consider this way. Correct? Okay, perpendicularly outward. Similarly, here also area vector you can draw perpendicularly outward. Got it? Fine. Now let us find out the amounts of electric fluxes linked with, say, this surface number 1, this surface number 2 and this curved surface number 3, one by one. Okay. Come on, phi 1 equals to, I told you whenever plane surface is lying in uniform electric field, you can go for finding electric flux using this formula A into E, correct? So phi 1 equals to A into, I am writing E1. Similarly, phi 2 equals to here A into E2, correct? But because this point and this point are equidistant from this plane of charge, the magnitudes of electric fields have to be same, and if these two magnitudes are same, let their common magnitude be shown by symbol capital E. So instead of E1 I am putting E, instead of E2 also I am putting E. What about electric flux linked with curved part? Let it be phi 3, okay? And according to general formula, it is integration E dA cos theta. Here I am writing E3, here I am writing dA3 cos theta, but theta is angle between area vector and electric field for this curved part. Now do one thing, on this curved part, you just select some area element, and for this area element, the perpendicularly outward area vector is like this, and so far electric field is concerned, I told you perpendicularly away. So it is like this, correct? Now angle between these two, you can see it is 90 degree. just put theta equal to 90 degree here. Cos 90 is 0, so the whole product is 0. And now according to Gauss theorem, the total electric flux linked with this cylindrical Gaussian surface would be phi equal to q upon epsilon 0. What is phi? Total electric flux, it has to be addition of all these three amounts of fluxes, phi 1 plus phi 2 plus phi 3. What about q? Q is the charge which is enclosed by considered Gaussian surface. Considered Gaussian surface is this, correct? Which encloses some charge here, correct? Fine. Now let us find out charge which is enclosed in this part. Let it be q. Then because this is surface charge distribution, we should recall surface charge density, and surface charge density is nothing but charge upon area. The charge enclosed in this part is suppose q, and the area of this part is the same as this area, is the same as this area, and these two areas we were taking each equal to capital A. So I am writing here capital A. Charge per unit area is called surface charge density. Find out q from here, transfer this. Q equals to sigma into A. Come on, q equals to sigma into A. Come on, q equals to sigma into A, correct? And now tell me, phi 1 and phi 2 are, phi 1 is A into E, phi 2 is A into E, so I am writing here A into E plus A into E, but phi 3 is 0, phi 3 is 0, and this part as it is. Now A into E plus A into E, altogether it is 2AE, right hand side is still the same, sigma A upon epsilon 0, sigma A upon epsilon 0. Now A will cancel, correct? So find out E now, transfer this 2 in the denominator, sigma upon 2 epsilon 0, sigma upon 2 epsilon 0, correct? E equals to sigma upon 2 epsilon 0, but what is sigma? Surface charge density, but for uniform surface charge distribution, surface charge density everywhere it is same and constant. So sigma is constant right now, epsilon 0 is as such constant only, so value of E in this case should be constant. And one more thing, it is not depending on the distance, whichever distance you may take from the plane of charge, irrespective of any value of distance, electric field produced by such an infinitely extended plane of charge would be same everywhere. And that is why if you plot a graph of electric field versus distance in this case, that graph will be like this, horizontal straight line, because though distance may increase or decrease, value of electric field is going to remain constant, constant equal to sigma upon 2 epsilon 0, correct? But one more thing, at whichever position the charge is located, exactly at that position it does not have its own electric field. So when you take r equal to 0 suppose, then you are exactly on the plane of charge, at that time you will not have any electric field. That's why I am putting some gap here, I am putting some gap here, correct? So in this gap I mean to say you cannot make r equal to 0, correct? And if you just slightly go away from the plane of charge, then you will have intensity of electric field which is sigma upon 2 epsilon 0, got it? But one more thing, you may take this distance very large, but in comparison with the distance, the dimensions of this plane must be taken almost infinite, correct? So if dimensions of plane of charge are very large as compared to the perpendicular distance from the plane of charge, then only this result can be applied, okay? Theoretically speaking, you can apply this result for infinitely extended plane of charge, okay, having uniform surface charge distribution with surface charge density equal to sigma, got it? Fine. My dears, in the discussion of previous topics, in Gujarati medium I had cracked 2 very good jokes, and I would like to tell you also that 2 jokes. Are you ready for that? Would you like to hear? Fine. See here, I told about cylindrical Gaussian surface, correct? You can think of a drum. You must have seen the drum, correct? In Gujarati it is called dhol. Now the drum has 2 sides, left side and this right side, I mean 2 ends, okay? There was a drummer and he was just giving the strokes very strongly, that too with a very high frequency, very rigorously. He was just beating both the sides of the drum, correct? Fatafat, very quickly. And that too he continued for a very long time. And the enthusiasm and the spirit which he had shown, it was remarkable. So people, they asked him that why today you are so much energetic. Then he just showed two faces of the drum, and on one face of the drum there was a photo of his wife, and on the other side of the drum there was a photo of his mother-in-law. So at home he couldn't do anything, then here he was just beating the photos, correct? And second thing here, this circle I have drawn just to make you realize about the depth of the figure, correct? Just to make you convinced with the 3 dimensions, okay? Fine. In Gujarati we call it gherao. Gherao means circumference, okay? Fine. There was a lady who was very fat, very fat. એ બેન બહુ જાડા હતા, કરેક્ટ? એનો જે ઘેરાવો હતો, ઘેરાવો એ બહુ મોટો હતો. તો એને જોઈને એક કવિથી રહેવાયું નહીં, એટલે કવિએ પેલા બેનને જોઈને કીધું કે બેન, જોઈને તમારો આ ઘેરાવો, જોઈને તમારો આ ઘેરાવો, કહેવાનું મન નથી થતું કે ઘેર આવો. એન્જોય ઇટ? જોઈને તમારો આ ઘેરાવો, કહેવાનું મન નથી થતું કે ઘેર આવો. Thank you. Come on, my dears, we proceed further. Let us see question number 39. It is about finding electric field due to two parallel planes of charge having infinite extent. Okay? At 3 different points. One point we are going to choose on the left side, another point in the middle region of these two, and third point on the right hand side. Okay, fine. Now these two planes have different surface charge densities. Say this first plane has surface charge density, say sigma 1, and second plane has surface charge density sigma 2. Just now we have obtained the formula for finding electric field due to infinitely extended plane of charge. Remember that formula? E equals to sigma upon 2 epsilon 0. Just use that formula. Instead of E, for first plane you write E1, and instead of sigma, for first plane you write sigma 1. Similarly, for second plane, instead of E1 you may write E2, instead of sigma 1 you may write sigma 2. Okay? And here, if sigma 1 is greater than sigma 2, if sigma 1 is greater than sigma 2, then E1 will be greater than E2. Correct? Fine. Now we are given 3 points. One is point P, another is point Q, third is point R. At each point, we are supposed to find out resultant electric field. Let us find out. For a plane of charge having positive charge, remember, what did I tell regarding the direction of electric field? Perpendicularly away, perpendicularly away. So at this very point, electric field due to first plane will be perpendicular to first plane and away from it. So it must be this way, perpendicular and away from this plane. So it must be this way, correct? Let it be E1. Similarly, at the same point, electric field due to second plane is also perpendicular and away, perpendicular and away. So that is E2. Okay? Now tell me, why I have shown this arrow longer and why this arrow shorter? Because sigma 1 is greater than sigma 2. When sigma 1 is greater than sigma 2, E1 is greater than E2. Because value of E1 is greater, I must show it by a longer arrow. Correct? Now at point P, both these electric fields are pointing in the same direction. And you know, two vectors, when they are linear and just when they are collinear and pointing in the same direction, to find out resultant vector, what we do? We make their scalar addition. We can make the addition like scalar. Because these two are in the same direction, we can make their addition in a scalar form this way. Resultant electric field at point P is the scalar addition of these two, that is E1 plus E2, correct? E1 plus E2 meaning thereby this plus this. So it must be this plus this, but when you take this plus this, you can take sigma 1 plus sigma 2 upon 2 epsilon 0. Sigma 1 plus 2 sigma 2 upon 2 epsilon 0. Sigma 1 plus sigma 2 upon 2 epsilon 0. But what about direction of this electric field? Here both these vectors are pointing in the same direction. So resultant electric field is also in the same direction, that is towards left side. That's why I am putting arrow towards left. Okay. Let us find out now resultant electric field at point Q. At point Q, due to this first plane, the direction of electric field is perpendicular and away. Perpendicular and away from this plane, so it must be this way, towards right hand side. Similarly, at the same point, due to second plane also, direction of electric field is perpendicular and away. Perpendicular and away, and that is E2, correct? Here also E1 is greater than E2, so here longer arrow and here shorter arrow. But because both the electric fields are pointing in the same direction, the resultant electric field at point Q can be written as scalar addition of these two, that is E1 plus E2. E1 plus E2. It is this plus this, so it must be this plus this. Again it is sigma 1 plus sigma 2 upon 2 epsilon 0, but resultant direction will be towards right hand side. That's why I am putting this arrow towards right hand side, correct? These two magnitudes are same, but directions are opposite. This is towards left, this is towards right, okay? What about resultant electric field at point R? At point R, the direction of electric field due to first plane is perpendicular to that plane and away from it, so it must be this way, that is E1. At the same point, direction of electric field because of second plane must be perpendicular to this plane and away from it, so it is this way, and this is towards left. Now here also E1 is greater than E2, so here longer arrow and here shorter arrow. Now tell me, because these two vectors are in opposite directions, then you can take their subtraction. And how should you take the subtraction? Bigger minus smaller, so it must be E1 minus E2. E1 minus E2. So I am writing here E1 minus E2, correct? And E1 minus E2 means this minus this, so it is this minus this. But when you take this minus this, then it is sigma 1 minus sigma 2 upon 2 epsilon 0. Sigma 1 minus sigma 2 upon 2 epsilon 0. And here the direction of resultant electric field will be in the direction of bigger electric field. Bigger electric field is this, it is towards right hand side, and hence this direction is also towards right hand side. Got it? Fine. This is most easy way. We are finding the magnitudes of electric fields and also the directions in a very easy way. Okay? Fine. Now we go for question number 40. It is about finding electric field for a spherical shell of charge. Spherical shell of charge. Actually, we had to discuss 4 applications of Gauss law. First was finding electric field due to infinitely long straight line of charge. Second was finding electric field due to infinitely extended plane of charge. Third is we are taking right now, it is about extremely thin spherical shell of charge. And fourth, sphere of charge. Fourth will be sphere of charge. Let us see one by one. 2 applications already we have discussed. Now here we are supposed to take extremely thin spherical shell of charge. I have not written extremely thin, but you must consider extremely thin spherical shell of charge. Extremely thin spherical shell of charge. Okay, fine. Just consider extremely thin spherical shell of charge as shown in the diagram here, having radius capital R. Okay. This spherical shell is completely made up of point charges. Let all of them be positive. You may take negative also, but at present we are taking positive. Fine. Now this is extremely thin, having radius capital R. Now we are supposed to find out electric fields in three different cases. First, in case of the region which is inside this cell, second, outside this cell, and third, on the surface of the cell. We will find out these electric fields one by one. Come on, first of all, for region inside this spherical shell. Now, in whichever region you want electric field, in that region you should consider Gaussian surface. So, I just imagine one spherical Gaussian surface which is concentric with this spherical shell of charge. So, they have their common center at this very point. Fine. Now, this considered Gaussian surface is S1 and its radius is this much, which is small r, which is less than this radius capital R. For region inside the spherical shell of charge, remember small r is less than capital R, okay? Then only you are inside, fine. Now apply Gauss law. What was that? Mathematical form, phi equals to q upon epsilon 0. Phi equals to q upon epsilon 0. Now what is Phi electric flux? Just remember its formula in words will be useful to you in many places. Phi is electric flux. In words you can say it is area, surface area into electric field. Surface area into electric field. For any radial electric field, which is the case here, you may use this formula, electric flux equals to surface area into electric field. Fine. Now this is the charge enclosed by considered Gaussian surface. Now considered Gaussian surface is this, correct? And there is no charge inside this surface. So no charge is enclosed by this considered Gaussian surface, and hence because q is 0, then 0 upon epsilon 0 will be 0. What is capital A? Surface area of considered Gaussian surface, and because it is spherical having radius small r, its surface area would be 4 pi into radius square, that is 4 pi small r square into E, and that must be equal to 0. Now from here you can infer that E must be 0, E must be 0 because neither 4 pi is 0 nor r is 0. So E must be 0. So what do we conclude now? For region inside this spherical shell of charge, the electric field is 0. Electric field is 0. Please remember this result will be useful to you in future. Okay. Now we talk about region outside this spherical shell. Outside this spherical shell. Look, consider one bigger spherical Gaussian surface which is concentric with given spherical shell of charge. So they have their common center at this very point. Fine. Let it be S2. And now apply Gauss law for that. Come on. Phi equals to q upon epsilon 0. What is phi? Electric flux for radial electric field. It is surface area into electric field. Surface area into electric field. Correct? Now this is the charge enclosed by considered Gaussian surface. Right now considered Gaussian surface is this. Correct? And the charge enclosed by it is this total charge of spherical shell of charge. Correct? Is the total charge contained in this spherical shell. Let it be small q. So this is the charge enclosed which is small q and divided by epsilon 0. Now what is A? Surface area of considered Gaussian surface. Considered Gaussian surface is this. Correct? Its radius is small r, and because it is spherical, the surface area would be 4 pi into radius square, 4 pi into radius square into E, that equals to q upon epsilon 0. Correct? Find out E from here. Transfer this 4 pi square in the denominator. So 1 upon 4 pi epsilon 0 into q upon r square. Correct? Now tell me, 1 upon 4 pi epsilon 0 can be replaced by small k into q upon r square. Correct? And can you recall E equals to kq upon r square? E equals to kq upon r square. Such an electric field was possessed by a point charge. Can you recall? So from here you can say, so far region outside the spherical shell of charge is concerned, the total charge of that shell behaves as if it is a point charge located at its center. I repeat, so far region outside the shell of charge is concerned, the total charge in spherical shell behaves as if it were a point charge located at its center. Correct? Fine. Now, from equation 1, come on, A is 4 pi r square into E. I want to place value of small q, which is total charge contained in the shell. Now, for this extremely thin spherical shell, you can say it has surface charge distribution, and if it has surface charge distribution, then you can recall surface charge density, which is sigma. It is charge upon area. Charge is small q, and surface area for this sphere having radius capital R is 4 pi capital R square. Find out small q from here, transfer this. So, it is 4 pi r square into sigma. Place this value of q over here. Come on, this q is 4 pi r square sigma, correct? This q, come on, this q is 4 pi r square sigma. This A is 4 pi r square into capital E divided by epsilon 0. Take care, this capital A is surface area of considered Gaussian surface. Considered Gaussian surface is this, correct? Its radius is small r. That's why I am putting here 4 pi small r square. And this is the charge enclosed by considered Gaussian surface. Charge enclosed by considered Gaussian surface. Considered Gaussian surface is this, and charge enclosed by it is this, which is the total charge contained in this spherical shell of charge, which is small q, which is 4 pi capital R square sigma. 4 pi capital R square sigma, correct? Divided by epsilon 0, as it is 4 pi will cancel. Find out capital E, it will be sigma upon epsilon 0 into capital R square upon small r square. Come on, sigma upon epsilon 0 into capital R square upon small r square. Got it? Give it equation number 3. Now we consider the case on the spherical shell, means on the surface of spherical shell, correct? And when you are on the surface of spherical shell, naturally r will be equal to capital R. So, in place of small r, when you write capital R in equation number 2 here, right, in place of small r write capital R here, then it is E equals to kq upon capital R square, E equals to kq upon capital R square, correct? And you may write small r equal to capital R here, then small r square will be capital R square will vanish, giving you sigma upon epsilon 0, sigma upon epsilon 0, correct? But remember, these are the formula to be applied for a point chosen on the surface of spherical shell of charge. Got it? Now we go for question number 41. Sphere of charge. Sphere of charge. Here, my dears, I would like to clarify one point. Even in the examinations of AIEEE, which is conducted at national level, they have committed this mistake. There is a difference between charged sphere and sphere of charge. There is a difference between charged sphere and sphere of charge. What sort of difference? I am showing you. If you have metallic sphere and if you make it charged, then that charge is deposited only on the surface. There is no charge inside that sphere, correct? So, when charge is present only on the surface, you can say it has surface charge distribution, correct? Fine. But right now I am not talking about charged sphere, I am talking about sphere of charge. It is a sphere made up of point charges, and because the entire sphere is made up of point charges, it has volume charge distribution, okay? Charged sphere has only surface charge distribution, whereas sphere of charge has volume charge distribution. Got it? Fine. In the entire world, there is only one example for sphere of charge, and that single example is nucleus of atom of any heavy element. If you consider nucleus of atom of any heavy element, then there are so many protons confined in a very small spherical volume, and because the protons are confined in a very small spherical volume, at that time it forms a sphere of positive charges, okay, fine. Now, in case of this sphere of charge, what is the electric field inside the sphere, on the surface of sphere and outside the sphere of charge. Let us see these electric fields one by one. Come on. Consider this as sphere of charge having radius capital R, correct? In this sphere, the total charge is suppose capital Q. Because it has radius R, the volume of sphere would be 4 upon 3 pi capital R cube, and charge upon volume will give you volume charge density, correct? Now, we select first case, that is inside this sphere, inside this sphere. We want to find out electric field inside this sphere, suppose here. Then for that sake, what you should do, you should think of spherical Gaussian surface having its center at the same point where there is a center of given sphere of charge, correct? So consider some concentric spherical Gaussian surface which is concentric with given sphere of charge, okay? Now let it be S1, and for that S1 surface, come on, this much is the radius which is less than capital R, less than capital R. When small r is less than capital R, you are inside this sphere of charge, got it? Apply Gauss law, phi equals to q upon epsilon 0. What is phi? Electric flux. For radial electric field, its formula is surface area into electric field. Surface area is A, electric field is E. This q is the charge enclosed by considered Gaussian surface. Considered Gaussian surface is this, and charge enclosed by it, let it be small q, okay? So I am writing here small q divided by epsilon 0, fine. And now what is capital A? Surface area of considered Gaussian surface. Considered Gaussian surface is this, its surface area having radius small r will be 4 pi into radius square into capital E as it is, and that equals to q upon epsilon 0, q upon epsilon 0. Find out capital E from here, transfer this 4 pi r square in the denominator. So now it is 1 upon 4 pi epsilon 0 small q upon small r square. But what is 1 upon 4 pi epsilon 0? It is nothing but small k. So I just replace this by small k into q upon r square. Wait, again replace this small k by 1 upon 4 pi epsilon 0. And what about small q? It is the charge enclosed by considered Gaussian surface. Considered Gaussian surface is right now this one, and charge enclosed by it I am taking as small q. Don't you know, charge upon volume will give you volume charge density. Volume of this considered Gaussian surface is 4 upon 3 pi small r cube, because its radius is small r, correct? Now find out q from here, transfer this. So small q will be 4 upon 3 pi r cube into rho. Small q is 4 upon 3 pi r cube into rho upon r square. And tell me now, 4 pi will cancel. Small r square getting cancelled from numerator and denominator. And now when you simplify, you will get rho upon 3 epsilon 0 into small r which is left in the numerator, okay? This small r is there in the numerator. Now this part is constant, and this part is constant. If you remove it, you may write E varies as r. When E varies as r, it shows direct proportionality relation, and in that case, when small r will increase, the strength of electric field will increase. As you go away from the center inside the sphere of charge, at that time electric field increases proportionately, okay? Now we take the region outside the sphere, and so we are considering bigger Gaussian surface which is also concentric with given sphere of charge. So they have their common center at this very point. And for this bigger Gaussian surface, come on, the charge enclosed by it would be total charge of this sphere of charge, total charge in this sphere, correct? And that total charge in this sphere is capital Q. So I must write capital Q upon epsilon 0. Gauss law, phi equals to q upon epsilon 0, but that q you must write here which is enclosed by considered Gaussian surface. Considered Gaussian surface is this, and charge enclosed by it is the charge contained in this sphere of charge which is given to us, and let it be capital Q, okay, fine. And now that divided by epsilon 0 will give you electric flux. linked with considered Gaussian surface. Wait. Phi equals to A into E, that is surface area into electric field. This right hand side as it is. What about capital A? Surface area of considered Gaussian surface. Considered Gaussian surface is right now this one, having radius small r, which is greater than capital R. Because it has radius small r and it is spherical, its surface area would be 4 pi small r square into capital E, and that equals to q upon epsilon 0. Got it? Now find out capital E from here, transfer this part in the denominator. So 1 upon 4 pi epsilon 0 into capital Q upon small r square. Tell me 1 upon 4 pi epsilon 0, you can replace it by small k into capital Q upon small r square. Once again we have got electric field very much like a point charge, correct? For a point charge, its electric field is also like this only, k into charge upon distance square, correct? And because we are getting same result here once again, we can say so far region outside the sphere of charge is concerned, the total charge contained in that sphere behaves as if it were a single point charge located at its center. Okay, I repeat, so far region outside the sphere of charge is concerned, the total charge contained in that sphere behaves as if it were a single point charge located at its center. Got it? Fine. Now small k, once again I am writing 1 upon 4 pi epsilon 0. This is capital Q, that is total charge of the sphere, and if you are making subject of the equation capital Q from here, you may find it this way, just transfer this. So capital Q when found out from here, it will be 4 upon 3 pi r cube into rho, 4 upon 3 pi r cube into rho, here it is, 4 upon 3 pi r cube into rho, and that divided by small r square, correct? Now 4 pi will cancel, then rho upon 3 epsilon 0 you can separate, and into bracket in multiplication capital R cube upon small r square, capital R cube upon small r square. Got it? Give it equation number 2. This is the electric field in terms of total charge of sphere, and this is the electric field in terms of volume charge density. Okay. Now we take the case on the surface of the sphere, and when you are talking about those points which are on the surface of sphere, naturally small r will become equal to capital R. When small r is equal to capital R, come on, replace small r here by capital R, then you will find kq upon capital R square, kq upon capital R square, correct? And when you write small r equal to capital R here, correct, then you get rho upon 3 epsilon 0 into capital R, rho upon 3 epsilon 0 into capital R. You may write small r equal to capital R here also, no problem. Then r cube upon r square, so r square is getting cancelled, capital R is left in the numerator, here it is. Okay, fine. But mind well, these two electric fields exist at those points which are on the surface of sphere of charge. Got it? Let us see now question number 42. We are going to plot two graphs, electric field versus distance from the center of spherical shell of charge and of sphere of charge. Let us see one by one. First we take for spherical shell of charge, and for spherical shell of charge, when you plot a graph of electric field versus distance from the center of spherical shell of charge, the graph is like this. Look, graph is like this, from here to here electric field is 0, and then after here electric field varies like this hyperbola. Why it is like that I am showing you. When you are talking about this region, for this region small r is less than capital R, because this value indicates r equals to r. When you are on the left side, small r is less than capital R. When small r is less than capital R, you are inside the spherical shell of charge. Small r less than capital R, small r less than capital R, you are inside the spherical shell of charge. At that time we had proved there is no electric field inside this shell of charge. Okay, so electric field was 0. And because in the inside region there is no electric field, I am writing E equal to 0, just put one horizontal line like this. Okay, fine. Now when you are on the surface, at that time, when you are on the surface, this electric field is maximum, which is kq upon capital R square. So this electric field is maximum, which is E maximum, kq upon capital R square. But then after, when you take this region where r is greater than capital R, when r is greater than capital R, you are outside the spherical shell of charge. For r greater than capital R, for r greater than capital R, you are outside the spherical shell of charge. At that time, electric field is this much. When these two are constants, the relation between E and R would be E varies as 1 upon r square. When E varies as 1 upon r square, it means to say when distance r will increase, electric field will decrease according to this hyperbola. So you are supposed to plot here hyperbola, correct? Fine. Please don't show this line as a solid line. Don't show this line as a solid line. You must show it like this, broken, okay? Because it is not a part of the graph. Graph is from here to here, and then after it is non-continuous, and then after again that graph starts from this point onwards. It is like a hyperbola, okay? Don't show this line a solid one, just show dotted or broken line like this, okay? Fine. Then we plot similar graph for sphere of charge. In case of sphere of charge, when you take small r less than capital R, you are inside the sphere, and for a region inside the sphere, tell me, this was the formula applicable. At that time we had proved E proportional to R, meaning thereby there is a direct proportionality relation, and in that case graph of E versus R would be a straight line, and the same straight line I have shown here, correct, up to R equal to capital R. And when you take R equal to capital R, at that time this is the electric field which is maximum, and that is the point on the peak where electric field is maximum, equal to K into capital Q upon capital R square. But further, if you take R greater than capital R, means you are outside the sphere, and when you are outside the sphere, R greater than capital R, at that time electric field varies like this, E varies as 1 upon small r square. When E varies as 1 upon small r square, again as this distance will increase, this electric field will decrease according to this hyperbola, okay? So up to this region, the graph is straight line, and then after it is a hyperbola, okay? Fine. With this, we mark the end to the theory part of this chapter, okay?